It's working. Looks like everything is working properly. There it is. All right, greetings, YouTube. Beautiful Mind here. We're continuing our discussion on chapter 2, exponential and logarithmic functions. And here we're going to be looking at section 2.4. We're going to look at some applications of log functions, right? Uninhibited and limited growth models. A couple of objectives. We like to find functions that satisfy dp by dt equal to k times p, all right? So basically like p prime equal to the constant times the original. And then we like to solve application problems using exponential growth and limited growth models. With this theorem number 9, a function y equals f of x satisfies the equation dy by dx equals k times y, or in other words, f prime equals some constant times the function. A function satisfies this if and only if it takes on this form, right? This is like the exponential growth model, right? For some constant c. Okay. So if we have the derivative equals some constant times the function, a function satisfies this equation if and only if it has a form similar to this, some constant times, basically the exponential growth model. But we're asked to find the general form of a function that satisfies this equation. So the derivative equals 5 times the original. Again, by theorem 9, the function must satisfy this form, right? Like this is just a direct application of theorem 9. We have some a prime equal to 5 times the original. So then it has to take on this form. If we take the derivative of this guy, we'll finish here, right? So we're just doing a direct application of theorem 9. Okay. For you all, just for the sake of time. So then we have this example on uninhibited population growth. So the equation dp by dt equals k times p, or p prime equals k times the original, is the basic model of uninhibited or unrestrained population growth. Whether the population is comprised of humans, bacteria in a culture, or dollars invested with interest compounded continuously. So then P of t equals c e to the kt, right? Or P of t equals p naught e to the kt. P naught, this means the initial conditions, right? Where c is the initial population P naught and t is the time, okay? Suppose that an amount P naught in dollars is invested into a savings account where the interest is compounded continuously at 7% per year. Man, if I had an interest-bearing account that has 7% interest per year, I would be halfway on my way to financial freedom, right? Okay, I think it's story time again. Let's see. So when I was a student at Morehouse, one evening I was attending a meeting in this honor society, and someone did a presentation claiming they were doing a fundraiser for something called the Infinite Scholarship, right? I was like, Infinite Scholarship? How do you have an infinite scholarship? It implies that there'd be money for the scholarship forever, right? So basically, the way it goes, they had an interest-bearing account. Like, okay, we can even use this one. Well, here, let's just be a little more modest, right? Suppose we had an interest-bearing account that had 5% interest per year, right? And we're just doing the lowest form of interest. So we had an interest-bearing account that earned 5% per year. They were doing a fundraiser to raise $1 million, right? So if you have an interest-bearing account that earns 5% per year, and you have a principal of $1 million, how much interest does that account earn every year just sitting, right? So then basically, long story short, we can use a simple interest formula, I equals PRT. So the interest earned is going to be that 1 million as a decimal 0.05, and the time is 1 year. So 5% of $1 million ends up being $50,000, right? The idea behind that, again, if you have an interest-bearing account that earns 5% interest every year, and if you had an initial deposit of $1 million, then that account just sitting earns $50,000 a year. That's essentially a full-time check. That's like right at about a couple of $1,000s a month, maybe a little bit more, just for sitting, right? So as long as every month you don't spend more than $2,000, which is a livable wage, it's very easy to not spend more than $2,000 in this day and age if you're not doing anything else, right? That's the thing about this, right? So like I was saying, that's why I got so excited. I was like, man, if I had an interest-bearing account that earns 7% or even 5% per year, that's why I said halfway, because it's basically two parts. You need an interest-bearing account that earns approximately 5%, and then you need a decent base. But again, if I was doing a fundraiser for an infinite scholarship, and as long as you only touch your interest earned and don't touch the principal, that's $2,000 a month. As long as that account is open, you just keep collecting it. All right. And again, this is the lowest form. So with those two initial conditions, I mean, if you play it, if you know what you're doing, you have money forever, for generations. And then once you get to a certain level, you can cause it to grow. You can create accounts like these for others and free other people. This is what I really, this is the intent that I have for myself. I actually went to the bank looking. Now, obviously, I don't have nowhere near that. So even if they had those kind of accounts, they weren't even shown to me, right? They wouldn't even like let me know that they offer these accounts. When I went, they were offering like 0.001%. Like the interest was so low. But it's different. Like once you actually reach those numbers, then you get access to it again. You can free yourself and have money for generations. And then you can truly live this realm the way I think it's meant to be lived. I don't think that we're meant to be here to punch a clock. And we're not, they always want to control us, enslave us, and have us working, making them rich. I'm like, but that's not what I'm here for, right? I mean, maybe there are people that is here for that, but I'm not one of them. I'm here to free myself and free as many people as I can. The sojourner truth of freedom, whatever. It's way too freedom. Ski appeal. the Harriet Tubman, the original free run. But anyway, so that's one of the goals. Like my dad showed that to me like decades ago. Yeah, I'm just aware of it, and I'm just trying to find my way. And there are ways to get there. Like there's so many different ways to get to those status, to get to that status. Okay, so let's get back to this one. Initial deposit is compound invested into an account that's compounded continuously at a rate of 7% per year. So then the balance P grows at a rate. So the rate of growth is 0.07 times P, right? So then we're asked to find a function that satisfies this. So we can use theorem 9. We have P prime equals some constant times the original. So this is going to be the exponential growth model. Find a function that satisfies this equation, write it in terms of P naught and 0.07. Okay, suppose that $10,000 is invested. What's the balance after 1 year? If 10,000 is invested, how fast is the balance growing? Okay, let me myself space. Did I lose my edits? Take some notes. Let's go here. That's fine. Or actually, we're given that dp by dt equals 0.07p in terms of p naught and 0.07. Okay. So then that theorem E is going to be what? P naught times E to some 0.07t. Growth model. It's kind of like PERT, PE to the RT, where P is the initial amount, or in this case, it's going to be P naught. The R from PERT is 0.07 and the time is in t. Okay, I think this is what they were looking for. I'm going to go with this. Suppose that $10,000 is invested. What's the balance after 1 year? Okay. The balance after 1 year, where P naught is going to be $10,000, times e to the 0.07. And this looks like a case for our trusty dusty rusty. Let me see this. It's going to do 10,000, 1, 2, 3 times what? E 0.07. Here, $25.08 approximately. So I'm going to say that this is approximately $7.25 cents. I was invested. How fast is the balance growing? So then for part C, it says how fast. That means what's the rate of growth after 1 year? It's going to be P prime of 1, right? Be 0.07 times that 10,000, that result we just got, 10,725.08. Just my trust. Rusty. So what I'm going to do is say that answer 0.07 is growing 750 per year. There we go. I'm going to say it's growing by that much per year. Okay. What do we do? Let's get rid of this. Can we P naught E to the 0.07T, P naught E to the, okay, and then we got the 725.08. I think we got that same thing. Then we got that it's growing by 750.76 per year, right? So after 1 year, the balance is growing at a rate of about 750.76 per year. Okay. All right. So then in this example, it says the world population was approximately 6.04 billion at the beginning of 2000. It's been estimated the population is growing exponentially at a rate of 0.016 or 1.6% per year. Thus, dp by dt equals 0.016p, where t is the time in years after the year 2000. So we're asked to find the function that satisfies the equation. Assume that p naught is this and k is this, okay? Let's go like this. estimate the world population at the beginning of the year 2020. Change of the population at the beginning of 2020. Okay. DP is 0.016 times P. So we can use that theorem 9. I'm just going to cut this. Our P of T, it says use P naught 6.04 for E to the R, the rate is 0.016 times T. Estimate the estimate the world population at the beginning of 2020. In other words, when T is 20. So ask to find P of 20, 6.04 E to the power of 0.016 times 20. Okay. Four times E to the power of 0.016 times 20. Approximately 8.32. 8.32. This is a billion people. Find the rate of change of the population at the beginning of 2020. Okay. P prime of 20, 0.016 times P of 20. So times that 8.32. So what I'm going to do is take my answer and say times 0.016. Is approximately billion people per year. 13.3. Let me look it up one time. .3%. Let me see. Is that billion? Billion people per year. So 0. Like billion. 0.133 billion people per year. Because at first I was thinking percent. First, we got the 6.04. Okay, I think we got that. And then for part B, 8.32 billion people. That, okay, that's fine. And then Zero. Okay, we got 0.133. So when you say 0.133 billion people per year, then you can rewrite it as million, 1.33 million people per year. That's fine. We got the same thing. We said it a little bit differently, but it's the same thing. Okay. Unrestrained or unrestricted exponential growth models. Right? So basically, it's like, these were models where the population was growing or restricted. It didn't like balance or it didn't level out as time progressed, right? So then a more realistic model is this, are models of limited growth. The logistic growth equation that you see given here is a model for population growth in which there are factors preventing the population from exceeding some limiting value L. Perhaps a limitation on food, living space, or other natural resources, right? So it'll essentially with these, they start off growing exponentially, but then they eventually level off because of some limiting factor. Okay, so this is the logistic growth model. Because it starts off initially like growing exponentially, and then it finishes growing logistically, like a log model. So in this example 4, you see spread, it says that spread by skin-to-skin contact or via shared towels or clothing, methicillin recitant, staphylococcus. I'm gonna try one more time. Staphylococcus, I think that's it. That's the best I can do. Staphylococcus aureus, MRSA, can easily spread a staph infection throughout a university. Left unchecked, the numbers of cases of MRSA on a university campus T weeks after the first cases occur can be modeled by this, right? So we have this logistic growth model. So then we're asked to find the number of infected students after 3 weeks, 40 weeks, 80 weeks, right? So let's see, T or T weeks. So basically we're plugging in those results into that model. Find the rate at which the disease is spreading after 20 weeks. We kind of need to, like, okay, we could take the derivative here. I'm probably just gonna, I'm kind of low tired. Let me see. Explain why an uninhibited growth model is inappropriate, but a logistic equation is appropriate for the situation. They use a calculator to graph the equation, okay? For part A, just plugging in 3 weeks, 40 weeks, and 80 weeks, you just plug it into that formula. Find the rate at which the disease is spreading after 20 weeks. So let's find n prime. So let me get a copy of this. I'm just gonna do, for part A, I'm just gonna kind of leave that as an exercise, but for part B, I want to look at this derivative, right? So I'm gonna get a copy of this model, and let's see if we can take the derivative. Let's explore the derivative here. Part B. So let me see. I think that might be simple enough. So then our n prime of t, so the bottom, which is this 1.1 plus 62.2 e to the negative 0.092 t. The bottom, okay, so the derivative of the top collapses all of this to 0, right? Because the derivative constant is 0. So I'm just going to get rid of this for now. So the bottom times the derivative of the top, and I'll just identify it as 0. Because again, what happened, if we say this times the derivative of the derivative of the top is 0. So then that first part collapses to 0, right? So we're going to say the bottom times the derivative of the top minus the top. Bottom, so then we do the derivative of the bottom. T2.2, so the derivative of E is itself, negative 0.092 t times the derivative of the exponent. .092, just close off my parentheses. So we said the bottom times the top minus the top times the bottom over the bottom squared. So we're going to have this 1 plus 62.2 e to the negative 0.092t quantity squared, right? We can simplify some of the numbers. And then it also asks us to find the rate after 20 weeks, right? So really what it's asking us to find is n prime of 20. Let me see if I can simplify this down a little bit more. So we have double negative becomes positive. Is this negative positive? I think I'm gonna just keep the original numbers. So then if we just kind of shift things around, we're gonna have this 568.803 times, there we got this 0.092, okay? Two times e to the negative 0.092t, right? Those are the numbers that we need to crunch. I just not crunch them right this second. And then the bottom, and we just need to replace t. Let me highlight it like this with the 20, right? So we're finding n prime of 20. So here times 20. We have this 1 plus 62.2 e to the negative 0.092, again, times 20. Say quantity squared. We're going to just use a calculator to crunch all this. So we're going to say this. Yeah. Let's do thing that I can do instead. Calculator. Will work. Okay, this is fine. So now let's just crunch all of this, right? So then first we have what? This 568 point. Let's share the screen. The numerator. So we're going to say divided by the denominator is 1 plus 60.09.